Hello everyone, my name is Neelu and I'm working as a research intern with Professor Graham Taylor on the topic of hierarchical object-centric learning. The research question that we are trying to address here is, can unsupervised hierarchical object-centric learning improve the scene decomposition and hence the scene understanding? To begin with, let's first take a look into the concept of object-centric learning from the unsupervised and self-supervised perspective. Most of the traditional neural network, they learn a single vector representing the entire scene. The major problem with such type of architecture is that context vector is quite entangled with the components of the scene. Such representation they are failing to generalize if same object appear in different contexts or environment. Because of this entanglement, it is very difficult to also generalize. It is also very difficult to interpret such representation. Object-centric learning, on the other hand, they learn multiple vectors instead of a single vector. So it is therefore easy to generalize that the same objects they are appearing in a different context. Interpreting these vectors are also much more easier as compared to the one which is learning a single vector. And the idea that I'm working on is basically building on top of object-centric learning, and we propose hierarchical object-centric learning. We call it as hierarchical OCL. So this concept is basically motivated by human-like understanding. We want to integrate such understanding into the neural networks. So we have different levels here. At level 1, which is holistic level, we only identify core structure, for example, identifying foreground in the background. At level 2, which is a semantic level, we would like to learn the representative vector for each class. For example, a single vector for all the classes of car, a single vector for all the person, and one vector for all the trees. And we can keep going. At level 3, which is a panoptic level, we would like to further disintegrate the semantic level. Here we learn a single vector for each instance of each class. For example, one vector for the car on the left, one vector for the car on the right, and we do the same procedure for all the objects present in the scene. Apart from this, we would also like to learn how different levels are related among each other. So in a way, we are learning a directional scene graph where we are encoding scene at different level of abstraction, and we know how to go towards it. Let's now see how we will gonna generate such framework. The task here is equivalent to the set prediction, where each set represents a group of pixels voting for a common concept. We perform such learning for each level and add the hierarchy part later on. The existing method, the state-of-the-art is proposing we have data which use supervision, which means we need labeled data along with the images input. And the neural perceptual grouping, which basically focus on clustering the objects in a scene. In unsupervised domain slot attention is basically a dominant method for this task, which automatically learned to kind of recognize those structures in the scene. So our approach uses slot attention as one of the core component. So slot attention, so let's see now what slot attention is. It is basically iterative and competitive attention, where each slot queries the input feature and finds a region belonging to the slot. So softmax is so basically we have 4 rows here, which corresponds to each slot, and as I mentioned that it is competitive and iterative. The competition come out of the fact that for each at the slot dimension we have the softmax function, which ensures that only one object is assigned to a single slot. And then it is an iterative process, which means over the time slots are getting refined. For example, at t equals to 1, the slots are not very well represented. But if we move across the time, we see that each slot is getting one object. So, author from the main paper, they integrated such attention with an auto-encoded network, where the task is the reconstruction of image itself. So, just to follow this architecture, we provide our input image to a CNN network, which encode the features, and then input to the slot attention module is CNN encoded feature and the slot itself. The slot here are randomly initialized, but slot attention module over the time it learns to assign each object to one of these slots. After that we pass those slot to the slot decoder, which take each of the slot individually and learns an alpha channel along with the decoded representation of each slot. And finally we combine, so alpha channel basically represent where the slot is active. So finally, we combine those decoded representation along with alpha channel to give the final slot reconstructed image. And the loss here we try to minimize is mean square error between the reconstructed image and the input image. So we adopted a similar idea except for the few modifications. Firstly, instead of image reconstruction, we are using feature reconstruction. For example, here we have input image and we encoded using Nano V2, and which a lot of the approaches these days are doing instead of, because feature space is much more I would say comprehensive as compared to the image space. So so instead of image reconstruction, we are focusing on feature reconstruction. And once we have the feature encoded from a large foundation model like Dino, we have a two-layer MLP to kind of bridge the gap between the space of slot attention and the foundation model representations. We also modified the slot attention module itself slightly. So instead of flat hierarchies, we have different levels. We have 3 levels, level 1, level 2, and level 3. As we move up in the level, we increase the number of slots because we want to decompose the scene into multiple objects as we move up in the hierarchy. So now, apart from the original reconstruction laws, we also add alignment laws, which means across the consecutive hierarchy, we want to ensure that if the slot from level 1, they have some association between the slot at the final grading. Because what basically we are doing is we are making the representation much more comprehensive by subdividing the objects in the lower levels. So just to give an idea about what the 2 loss function that we are using in our approach. So for the reconstruction loss, we are using mean square error between the original and the reconstructed feature. And for the alignment loss, we are using we are clipping across the dimension of affinity matrix. So we are computing the affinity matrix between the child and the parent slot, where M and N here represent child and parent slot itself. So it measures the similarity between each of the child slot and the parent slot. And then we do the thresholding to get the idea what are the assignments. And we penalize when the parent slot fails to win even a single slot from the children slots. In this way, we ensure that the alignment is regularized. So the total loss function will be the combination of reconstruction and alignment loss, along with the factor of lambda, which is a hyperparameter here. And for our experiment, we started with a value of 0, and then we keep on increasing the value of lambda, because in the beginning, we have slots are being assigned with very low probability. So we wait for some time so that they form, they choose for some object, and then we add this alignment loss gradually. So here are some results. I don't know, it's really blurry. I'll just try to go through it, but okay. So we measure the results on we evaluate the result on unsupervised object discovery task using 4 evaluation metrics. So first two represent the ARI, and the second one is MIOU, and the last graph is for the MBO. So ARI measures how good the clustering is, and on the first two graphs we have ARI, which is measuring both the foreground and background. The first graph measures consider both foreground and background, but the second graph only consider the foreground clustering. Take the foreground clustering into the consideration. And the last two are the main metrics, which determines that how good is a segmentation using our slot representations. And the last one is for the object-centric, is MBO, which actually main metrics for object discovery. So basically MIOU and MBO, they are same, except for the fact that MIOU chooses one slot for each object, where MBO chooses MBO relaxes this constraint a bit. We can have 2 slots for one object as well. So on the x-axis, we have different baseline methods, and the last column, basically, which was supposed to be, which is HSA, is our method. And I see that the numbers are not quite visible here, but on three out of these 4 metrics, ARI, MIU, and MBO, we have significant improvement. The performance improvement is almost double as compared to the baselines. On one metric, which is ARI foreground, we still have some improvement, but it is not as significant as on the other metrics. So next step, we already have some improvement on the task of object discovery. So we would like to use such method for more expressive vision task. And one such task is unsupervised scene retrieval. So most of the method for unsupervised scene retrieval, they are using scene graph, and scene graph is shown on the left, where the main requirement for the scene graph is it needs object and relation labels. So there is a high annotation cost. We need to kind of figure out what are the objects and what are the relationship between them. On the left, we have our hierarchical slot attention method, where we have such not similar encoding, but some sort of scene decomposition scene graph, which is learned implicitly by our method. So we are not implicitly learning those labels, and we do not have any annotation cost here as well. So basically, in unsupervised way, we are retrieving the scene from the bunch of images. And so the lab where I'm working, they are working quite a lot with biodiversity monitoring. So another use case that I thought about using this method is for actually analyzing the scene where we have bulk of objects. Here objects are multiple insects. So learning the flat representation might not be meaningful here, because we cannot comprehend what are the classes and how many of each species exist for each class. And we are actually interested in doing such kind of, comprehensive reasoning. So I believe that we kind of decompose a scene into multiple hierarchies. We can do such sort of reasoning pretty easily. And another problem with our slot addition method is that we have it is only workable for a limited amount of object, but once we kind of decompose it this way, it makes the problem much more simpler and can make scalable for such a difficult data set. Yeah. So to summarize, we propose hierarchical object-centric learning, an approach called hierarchical object-centric learning. It is much more interpretable. It has human-like scene decomposition. We have some preliminary results on object discovery task, and next steps are evaluating on more expressive tasks like scene retrieval and having a comprehensive reasoning on mask ID 45 dataset. So this is it from my side. Thank you for your time. Any questions?
Thanks, Neelu. Great explanation. I was just curious, if you could just walk us through maybe one application area for your methodology, and maybe you can comment on what's fundamental problem with the current approach that your solution is trying to solve.
Yeah, so actually we all the current approaches they consider they do not offer such kind of scene reasoning where we go at different levels. So they only decompose a scene into flat hierarchies, flat objects. And sometimes I feel like the decomposition does not, the task is object discovery, the decomposition does not make sense because what happens is some of the objects, they are kind of over disintegrated and some are under disintegrated. But I feel like that once we ensure this such sort of alignment, especially background, and that's why we have, as we see here in this graph, this is for computing ARI for both foreground and background, and this is only for the foreground, right? So foreground objects, we are doing fine in terms of the foreground objects. For example, I showed a scene where we have cars and trees. It was fine, but when the scene got complicated, the background objects, they have a tendency to disintegrate into multiple objects with current unsupervised learning method. And I feel like we have improved quite a lot on that using our hierarchical method.
Thanks so much.
Thank you.